Settle in and get comfortable for a slow, sleep-friendly journey through the story of Venus. If you enjoy these calm space stories, take a second to like the video and subscribe, and drop a comment telling me where you're listening from tonight. Now lower your lights, get cozy, and let your mind drift as we move gently through a world that looks bright and peaceful from far away. But up close is one of the most intense places in the solar system. Venus, the planet that teaches you how misleading first impressions can be, because everything about it is wrapped in a thick veil that hides the surface, hides the sky, hides the details, and forces you to imagine it through pressure, heat, chemistry, and time. Venus is almost Earth's twin in size, and that's the trap. You hear similar size, and your brain wants to assume similar world, but Venus is the opposite lesson. Same neighborhood, same basic building blocks, completely different outcome, and the difference is not one single thing. It's a chain of feedback loops that locked in and never let go. Venus sits closer to the Sun, and that alone shifts the energy balance. But the real story is the atmosphere. A deep, heavy blanket of carbon dioxide with clouds made mostly of sulfuric acid, so thick that sunlight doesn't just warm the ground and bounce back out the way it does on Earth. It gets scattered and trapped, and any heat that tries to leave gets swallowed and returned over and over until the surface becomes an oven. If Earth is a planet with an atmosphere, Venus is a planet buried under an atmosphere, and you can't talk about Venus without talking about pressure first, because the pressure at the surface is crushing, far beyond anything a human body could survive, like being deep under an ocean. Except the ocean is gas, and the gas is hot enough to soften metal. That pressure changes everything: how rocks behave, how winds work, how temperature moves, how chemistry runs. It's not just thick air. It's an entirely different physical environment, a place where the line between atmosphere and surface feels less like a boundary and more like a heavy weight pressing the planet into a constant slow squeeze. And above that surface sits the cloud layer, bright and reflective, which is why Venus is so luminous in our sky. From Earth, Venus can be the evening star or morning star, shining as a calm, bright point. But that brightness is basically the planet's mask, sunlight bouncing off acid clouds. Those clouds don't just float harmlessly. They are part of a chemical cycle involving sulfur compounds, sunlight, and atmospheric circulation. And they create a world where the sky is never clear, where the sun would be a diffuse glow at best from the ground, if you could stand there at all. The upper atmosphere is also where you find one of Venus's strangest tricks: superrotation. Venus rotates slowly, painfully slowly, taking longer than Earth to spin once, yet the atmosphere high above races around the planet incredibly fast, lapping the globe in just a few days. Like the sky itself is impatient even when the planet beneath it barely turns. That means if you imagined standing on Venus's surface, the day in terms of sunlight changes is weird, drawn out, and slow. But above you, the winds at cloud level are tearing around the planet at speeds that don't feel possible, and the reason that can happen is because a thick atmosphere can store and transport momentum, and because heating differences and wave patterns can pump energy into those fast winds, creating a planet-scale circulation that becomes its own machine. Venus is basically a locked box of gas with a fast-moving lid, and the details of that motion are still being studied because Venus is hard to study. Everything you do gets blocked or burned or crushed. That's why Venus's surface stayed mysterious for so long. You can't see through those clouds with normal light. You need radar to map the surface, and when we finally did, we found a world that isn't a simple cratered dead rock. Venus has mountains, vast plains, strange volcanic features, and evidence that volcanism has shaped large parts of the surface. It looks like a world that has been resurfaced, as if huge areas were repaved by lava flows at some point in its past, burying older craters and creating a surface that looks geologically young in places. The crater count on Venus isn't what you'd expect from an ancient, untouched surface. There aren't as many craters as a dead world should have, suggesting that Venus has been active enough to erase them, and that activity likely involves volcanism and tectonic deformation, but in a style that doesn't match Earth. Earth has plate tectonics, moving plates recycling crust. Venus seems to operate differently. It has tectonic features, but not the same global plate system. Instead, Venus might release its internal heat through episodic resurfacing, long periods of build-up, then large-scale volcanic events that renew huge regions. Imagine a planet trying to get rid of heat, but without the same plate machinery Earth uses, so the heat builds pressure beneath a stiff lid until the lid gives way in bursts. That's not confirmed in every detail, but it's a powerful way to picture Venus, a world with a rigid shell over a hot interior, where the planet's energy has nowhere to go easily, so it expresses itself through strange geology. And because the surface is so hot, rocks may behave differently. At Venus temperatures, certain materials can soften, chemical reactions can run faster, and the boundary between geology and chemistry blurs in ways that are hard to intuit from Earth. Even the air interacts with rock more aggressively. On Earth, oxygen and water do a lot of the surface chemistry. On Venus, the chemistry is dominated by carbon dioxide, sulfur compounds, and extreme heat, so weathering and surface alteration would follow different rules, and the planet's appearance and reflectivity could be shaped by chemical coatings that form and change under those conditions. Venus is a world where air is heavy enough to sculpt behavior, and heat is constant enough to be a landscape feature all by itself. And then there's the water question, the haunting one, because Venus may not have always been like this. There are models that suggest early Venus could have had more temperate conditions, maybe even oceans, and if that's true, then the shift into the current greenhouse state becomes one of the most important cautionary stories in the solar system. How a planet near Earth's size can diverge into a runaway greenhouse. The basic idea is that being closer to the sun raises temperatures, which increases water vapor in the atmosphere if water exists, and water vapor is a greenhouse gas, so more heat means more vapor. More vapor means more trapping means more heat. A feedback loop. If that loop runs away, oceans can evaporate, the atmosphere can become saturated with vapor, and sunlight can break water molecules apart high in the atmosphere, allowing hydrogen to escape to space, slowly stripping the planet of water. What remains is a dry world with a thick CO2 atmosphere, because without oceans and without a mechanism to lock carbon away, carbon dioxide accumulates. Earth has carbon cycles, oceans dissolving CO2, rocks storing carbon, biology helping regulate. Venus lacks those stabilizers now. If Venus lost its water early enough, it lost its thermostat. And once the thermostat is gone, the planet can drift into an extreme state and stay there. That's why Venus is not just hot. It's a record of how planetary climate can lock into an outcome. The planet doesn't wake up one day and decide to become hellish. It gets nudged, feedback amplifies, stabilizers fail, and the new state becomes self-sustaining. Venus's clouds, for example, reflect sunlight, which could cool the planet, but the greenhouse effect below is so strong that the net result still locks in heat. And the thickness of the atmosphere means heat is distributed efficiently across the globe. So Venus doesn't have a day side roasting and a night side freezing the way a thin atmosphere world might. Venus is hot everywhere because the atmosphere is too good at sharing. Even the slow rotation ties into this. A slow spin changes circulation patterns, changes cloud behavior, changes how heat moves, and may have influenced how the climate evolved over time. Venus rotates so slowly that its solar day, the time between sunrises, is extremely long, and yet because of the atmospheric circulation, the temperature doesn't swing wildly the way you might expect. The whole planet sits in a thick thermal bath. Another strange detail is that Venus rotates in the opposite direction compared to most planets, retrograde, so the Sun would appear to move differently across the sky compared to Earth, and if you care about the feeling of the world, that retrograde spin makes Venus feel like it runs backward, not in a supernatural way, but in a quiet, mechanical way that adds to its alien mood. It's like everything about Venus is slightly off from what your brain expects. The twin of Earth that became the reverse of Earth, the bright star that hides an acid sky, the slow spinner with a racing atmosphere, the planet with volcano-like features but without Earth-style plates, the world that might have had water but now is dry and sealed. And because the clouds hide the surface, Venus becomes a planet you experience mostly through inference. Radar maps, atmospheric probes, spectroscopy, and the brief survival of landers that tried to endure conditions that destroy electronics. Those landers are like moments of contact, short transmissions from a place too harsh to stay, showing rocks, showing a horizon under a dim, yellow-brown sky, giving proof that the surface is real and not just a number on a chart. And that dim horizon image is one of the most calming ways to imagine Venus without getting anxious. Not the hell planet cliché, but the quiet heaviness of a sealed world. Picture standing on a plain of dark rock under a dense sky. The light is muted, not sharp. The clouds above are thick, layered, and endless. The air is heavy, pressing down like an invisible ocean. The horizon is close because haze and density swallow distance. There's no blue sky, no wind you can feel like a breeze, just the idea of movement above in the fast cloud layer, while down here the world is static, slow, and unyielding. Venus is like a planet that put itself in a pressure chamber and never opened the door again. And even with all that intensity, Venus is not evil. It's just physics. It's what happens when feedback loops run without a regulator, when water doesn't persist, when carbon dioxide dominates, when sunlight and chemistry shape clouds that hide everything underneath. The reason Venus matters, beyond the drama, is that it gives you a comparison point for Earth. Two similar-size worlds, radically different. That contrast makes you appreciate how fragile habitable is, not as a moral thing, but as a balancing act. It also makes Venus one of the best worlds for sleep storytelling, because you can drift through the layers, the reflective clouds high above, the super-rotating winds racing around the planet, the chemistry building sulfuric acid droplets, the dim light filtering down, the crushing pressure near the surface, the hot rocks, the radar-revealed mountains and volcanic plains, the slow retrograde spin turning the planet like it's moving against the solar system's usual flow, and behind it all, the question of the past. Whether Venus ever had oceans, and if it did, how a world can lose them and become something else entirely. As you listen, you don't need to hold on to the scary parts, just hold on to the steadiness. Venus is consistent. It doesn't surprise you with sudden changes. It's a world of constant conditions and slow planet-scale cycles. Clouds circulate, chemistry runs, heat stays trapped. The surface sits under that weight. The whole planet glows softly in our sky like a calm light, while underneath the brightness is a sealed story written in gas and stone. Let that contradiction slow your thoughts down. Let the idea of layers, clouds, winds, chemistry, pressure, rock, stack gently in your mind like a quiet descent through a thick atmosphere, until your thoughts stop trying to jump ahead and just drift, one layer at a time, deeper into stillness. Venus has a way of making simple ideas feel complicated, because the moment you try to explain why it's so hot, you realize you're not talking about one cause, you're talking about a chain reaction that locked into place and never reversed, and the easiest way to fall asleep to Venus is to treat it like a slow, sealed system, like a greenhouse that got too efficient then never opened a window again. The baseline fact is that Venus is dominated by a massive carbon dioxide atmosphere. CO2 is good at absorbing and re-emitting infrared radiation, which is the kind of heat a planet tries to radiate back to space. If you thicken the CO2 blanket enough, you trap more outgoing heat, the surface warms, and as the surface warms, it radiates more infrared, which the CO2 absorbs and sends back down, so the planet stabilizes at a much higher temperature. That's the textbook greenhouse effect. But Venus isn't textbook, because the atmosphere is so thick and so massive that it behaves less like air and more like a deep, compressible fluid ocean of gas. Pressure at the surface is enormous, and pressure itself matters because it increases the capacity of the lower atmosphere to hold heat, and it changes how gases behave. It's not that pressure creates the heat directly in a magical way. It's that pressure and greenhouse trapping together produce a lower atmosphere that holds on to thermal energy and distributes it efficiently, creating a world that doesn't cool easily anywhere. On Venus, heat isn't trapped in one region. The thick atmosphere moves it around. That's why you don't get a crisp, hot day side and a cold night side. The planet becomes a nearly uniform thermal bath. Even with slow rotation, the temperature stays high across the globe because the atmosphere is too good at sharing. A thin atmosphere would allow big swings. Venus doesn't allow swings. It smothers them. Now add the runaway feedback that likely drove Venus into this state. If early Venus had significant water, then being closer to the sun would raise temperatures, which increases water vapor in the atmosphere. Water vapor is itself a greenhouse gas, so more vapor means more heat. More heat means more vapor, and that spiral can accelerate until oceans evaporate and the atmosphere becomes saturated with steam. Once water vapor reaches high altitudes, ultraviolet sunlight can break water molecules apart. Hydrogen, being light, can escape to space more easily, leaving oxygen behind, and the oxygen can react with surface materials. Over long time, you can lose water permanently. If that happens, you lose one of the most important climate regulators a rocky planet can have, a big surface reservoir that can dissolve gases, drive weathering, and participate in carbon cycling. Earth's long-term carbon cycle depends heavily on water, oceans dissolving CO2, rain weathering rocks, carbon being locked into minerals, and tectonics recycling it. If Venus lost its water early enough, it lost its ability to lock CO2 away. Then CO2 accumulates, not necessarily instantly but persistently. Volcanoes and outgassing keep feeding it. Without an efficient sink, it stays. Over time, you build a thick CO2 atmosphere. Once it's thick, it traps heat strongly. Once heat is strongly trapped, the surface becomes hostile to anything that would have helped remove CO2, like liquid water or Earth-style weathering. That's how a planet can get stuck. The conditions that could cool it are the first things the planet destroys as it warms. It's the ultimate lock-in. Venus becomes a self-maintaining greenhouse, not because it wants to, but because the feedback loop changes the rules of the system. Venus's clouds are the part that confuses people, because clouds can cool a planet by reflecting sunlight, and Venus's cloud deck is extremely reflective. It bounces a lot of sunlight back to space. So why doesn't that save Venus? Because the greenhouse trapping below is so strong that even with high reflectivity, the net energy balance still leads to extreme surface temperatures. Think of it like this. The top of Venus's atmosphere reflects a lot of sunlight, but what does get in is trapped efficiently, and the lower atmosphere is so thick that heat can't escape from the surface easily. The surface is basically trying to radiate heat into a wall. Meanwhile, the clouds themselves are not water clouds. They are mostly sulfuric acid droplets suspended in the upper atmosphere, created from sulfur compounds interacting with sunlight and atmospheric chemistry. Those droplets form an unbroken veil that hides the surface in visible light and makes Venus look bright and smooth from afar. That brightness is why Venus is such a striking object in our sky, morning star, evening star, But up close, it's not a calm, bright world. It's a masked one. Above the clouds, Venus can look almost serene. Below them, the planet is relentless. The sulfur story matters because it implies active chemical cycling and possibly active volcanism. Sulfur dioxide in the atmosphere can be produced by volcanic outgassing, and in the upper atmosphere it can help form sulfuric acid. If volcanic activity changes, atmospheric sulfur compounds could change too. That means Venus's cloud chemistry could be linked to internal geology. And Venus's surface geology is weird in the best way. Radar mapping shows vast plains, large volcanic constructs, and features that look like lava flows and volcanic domes, plus strange circular and oval structures that don't neatly match Earth's categories. Venus doesn't show Earth-style plate tectonics clearly. Instead, it may operate with a stagnant lid, one big crustal shell that doesn't break into mobile plates. And if that's true, then internal heat builds up under that lid. A planet still has to lose heat. If it can't lose heat through plate tectonics, it may lose it through episodic, catastrophic resurfacing events where huge amounts of lava flood the surface and reset large areas, burying craters and leaving a relatively young-looking surface. That idea fits the crater distribution. Venus has fewer craters than a dead ancient surface would. The surface appears to have been resurfaced on a planet-wide scale at some point. Whether it was one major event or multiple episodes is still debated, but the concept is consistent. Venus might release its internal heat in bursts. Heat builds, pressure builds, then the lid gives way. The result is a planet that can look geologically young, even while being surface hostile. Venus also has a rotation that makes it feel like it's doing everything backwards. It spins slowly and in the retrograde direction compared to most planets. The exact reason for that isn't fully pinned down. Big impacts and tidal interactions are candidates, but the consequence is a weird solar day cycle. Yet the atmosphere doesn't care. The atmosphere super-rotates. This is one of Venus's most hypnotic facts. The solid planet rotates so slowly that a single spin is longer than a Venus year in one sense. But the cloud tops race around the world in just a few days. Superrotation means the atmosphere is circulating far faster than the ground beneath, like the sky is a fast conveyor belt sliding over a barely turning sphere. How does that happen? Thick atmospheres can develop strong global circulation patterns driven by heating differences and wave dynamics that transport momentum. Thermal tides, waves created by periodic heating, can push momentum into the flow. Planetary-scale waves can redistribute angular momentum. The details are complex, but the big picture is simple. Venus's atmosphere is a machine that can accelerate itself, and once it's running, it keeps running. It's a planet where the sky is the moving part and the ground is the stationary part. Another layer, Venus's surface pressure and temperature are so high that many familiar physical processes shift. The boundary layer near the ground behaves differently. Sound travels differently. Heat transfer is dominated by different mechanisms. Chemical reactions that are slow on Earth can happen faster. Materials can corrode quickly. A lander that touches down experiences a world that is not just hot, but chemically aggressive and mechanically crushing. That's why early landers survived only a short time. They didn't fail because engineers were bad. They failed because Venus is designed to kill hardware. Yet for those brief windows, they returned images and data that made the planet feel less abstract. Rocks, soil, a dim horizon under thick air. The light at the surface would be muted and yellowish because clouds scatter and absorb. Shadows would be soft. The sun would not be a clear disk. It would be a bright patch of diffuse light above an endless haze. It's not a dramatic fire scene. It's a quiet pressure scene. The kind of environment where nothing looks violent but everything is hostile. That contrast is part of the Venus sleep story vibe. Venus isn't loud. Venus is heavy. The planet's biggest feature is the weight of its atmosphere and the inevitability of its trapped heat. You can also think of Venus as a lesson in boundary conditions. Earth sits in a range where water can be stable as liquid on the surface for a long time. That one fact powers most of Earth's climate regulation. Venus sits closer to the Sun. Small differences in starting conditions or early events, how much water was present, how fast the planet cooled, how its atmosphere evolved, could push it into a different attractor state. Once it's in that state, it's hard to escape. The planet becomes an example of climate hysteresis. You don't just reverse the conditions and instantly return to the old state, because the system changes as it evolves. Lose your oceans, and you can't easily get them back. Build a massive CO2 atmosphere, and you trap heat so strongly that liquid water can't reappear, which prevents the sinks that could remove CO2, so the CO2 stays. It's not a loop you casually undo. It's a lock. The gentle way to imagine all of this is to picture Venus as layers. The bright, reflective cloud deck high above, a fast-moving sky sliding around the planet, chemical cycles creating acid droplets, sunlight filtered into a diffuse glow, and far below, a surface hidden in radar maps and short lander glimpses, dark volcanic plains and ridges under crushing pressure, an atmosphere thick enough to feel like a weight on the world, and heat that never really leaves. If you let your mind drift through those layers slowly, Venus stops being a scary headline and becomes a steady system. Sunlight in, reflection out, heat trapped, clouds circulating, chemistry running, surface waiting in dim orange light. No urgency, no sharp changes, just a planet in a stable extreme equilibrium, quietly, maintaining the same conditions for long stretches of time. Let that steadiness do what it does best. Flatten out your thoughts until they become as slow and quiet as the world itself. Venus's surface is a place you mostly have to imagine through indirect senses, because the planet refuses to show you its face in normal light. The cloud deck is so thick and so continuous that if you looked at Venus with your eyes from space, you'd see a bright, smooth, almost featureless sphere, like a pearl with subtle streaks. And that's the trick. The surface is hidden. So the way humans learned Venus's surface is through radar, sending radio waves through the clouds, bouncing them off the ground, and building maps from the echoes. That alone changes the feeling of the planet. Earth shows you its surface proudly. Venus forces you to decode it. And when we finally decoded it, the surface didn't read like a dead, cratered rock. It read like a world that had been worked over by internal heat and volcanism, a world with broad plains, highlands, ridges, and strange volcanic forms that don't always fit cleanly into Earth categories because Venus runs the same physics but under different conditions and likely with different tectonic rules. A lot of Venus is covered in volcanic plains, huge areas that appear to be basaltic lava flows that flooded lowlands and spread out, burying older terrains. There are large volcanic constructs too, including massive shield volcanoes, and there are features that look like lava channels and flow fields. But Venus is not simply a planet of volcanoes. It's a planet that seems to have been resurfaced, possibly on a global scale, because the distribution of impact craters is unusual. Venus doesn't have a huge range of crater ages with ancient terrains absolutely saturated. Instead, craters are relatively evenly distributed and not overly abundant, which suggests that much of the surface may have been renewed in the geologically recent past. The common picture that emerges is that Venus may go through episodes, long periods where heat builds up under a relatively immobile crust, followed by periods where massive volcanism and tectonic deformation release that heat and repave large portions of the surface. If Earth is a world where the crust is constantly recycling through plate tectonics, Venus might be a world where the crust is more like a single lid, a stagnant shell that can hold in heat until it fails in bursts. That's not the only model, but it's a powerful mental frame because it explains why the surface can look relatively young without needing Earth-style plates. Earth bleeds heat steadily through moving plates and volcanism along boundaries. Venus might hold heat and then dump it in episodes. You can imagine a slow simmer under a sealed lid, then a release. And that gives Venus a strange kind of rhythm. Quiet, then catastrophic, then quiet again. Except the timescales are so long it all feels like stillness to us. Another surface trait that makes Venus feel different is the way water is missing. On Earth, water sculpts everything. Rivers carve valleys, rain drives erosion, oceans shape coastlines. On Venus, liquid water cannot exist at the surface today. That means no river networks, no rain-driven landscapes, no ocean basins filled with water. Surface shaping is dominated by volcanic emplacement, tectonic deformation, and chemical weathering driven by hot CO2 and sulfur compounds. So Venus's surface can look sharp and preserved in some ways because it lacks water-based erosion, but it can also be chemically altered because the atmosphere is aggressive. The heat and pressure allow reactions that would be slow on Earth to happen faster, potentially forming mineral coatings that change radar reflectivity. In fact, one of the more intriguing observations in radar data is that some high-elevation regions appear unusually reflective, which has led to ideas that certain minerals might form frost or deposits at higher elevations where temperatures and chemical conditions differ slightly. It's not like snow in the human sense, but the concept is similar. A substance that is stable only in certain temperature-pressure chemistry windows could accumulate in highlands. Even if the exact substance is debated, the idea is soothing because it shows Venus still has gradients. Even in a world of uniform heat, altitude matters. Then there are the uniquely Venusian tectonic features. Venus has ridge belts, long, elevated, deformed regions that look like the crust has been squeezed and folded. It has rift zones, too, long troughs and fractures where the crust seems to have been pulled apart. On Earth, rifts can be places where plates separate and magma rises. On Venus, you can have rifting without global plate tectonics, through mantle upwelling pushing the crust apart locally. Venus also has vast networks of fractures, cracks that trace stress patterns. And then there are coronae, one of the most characteristic Venus surface forms. Huge circular or oval features with concentric fractures and ridges, often hundreds of kilometers across, thought to be created by mantle plumes rising and deforming the crust, then collapsing or changing as the plume evolves. Coronae are like fingerprints of the mantle pushing on the surface from below, and they're deeply Venusian because they reflect a world where the crust behaves as one large shell responding to upwellings rather than as a set of moving plates. You can picture Venus's interior as a slow convective engine. Hot material rises in places, pushing up the crust, cracking it, maybe producing volcanism, then cooling and sinking elsewhere, and the surface records those pushes as ridges, rifts, and circular fracture structures. Another reason Venus's surface feels mysterious is that we don't have many direct images. The landers that touched down lasted briefly. Their images show rocks and a dim horizon under thick yellowish light. The surface looks like a barren volcanic field, flattish in places with scattered rocks, no plants, no water, no dramatic sky. The drama is invisible, pressure crushing, heat baking, chemistry corroding. That makes Venus a planet of quiet menace, but for sleep narration you don't lean into menace, you lean into the hush. Imagine the surface as a dim, orange-brown world, a place where distance fades quickly because the atmosphere is dense, where the sky is always overcast with no direct sun, where shadows are soft, where wind at ground level might be present but not like a breeze you'd recognize, because the air is thick and the planet's rotation is slow, so everything feels heavy and damp in a non-water way, like being in a pressure chamber. Above you, high in the cloud tops, the winds scream around the planet in super rotation. Down here, the planet's surface sits under the weight of that atmosphere like it's pinned. Yet the surface is not passive. It bears signs of volcanic renewal. It bears signs of tectonic stress. It bears signs that heat from within has shaped it repeatedly. And that internal heat matters because it ties back to the atmosphere. Venus's atmosphere likely wasn't always as extreme. Volcanism can outgas CO2 and sulfur compounds. Over long time, if CO2 is not removed by oceans and carbon cycling, it accumulates. If water is lost, the sinks vanish. So the surface and the sky become partners in a locked state. The interior feeds gases, the atmosphere traps heat. The heat changes surface chemistry and prevents water-based regulation, and the system stays stable in its extreme form. Venus is also the reason people keep asking whether it's active today. Are there eruptions now? Are there volcanic plumes? Do sulfur dioxide levels vary? Are there thermal anomalies? These questions exist because the surface looks like it could have been resurfaced relatively recently, and because the atmosphere's chemistry suggests ongoing supply of certain gases. Some observations have hinted at changes that could be explained by active volcanism, but pinning down current activity is difficult because the clouds and the environment make direct confirmation hard. Still, you don't need active right now for Venus to feel alive as a story. The planet is a living record of internal heat and atmospheric lock-in, and the surface is the page that got rewritten enough times to leave you a mystery. How often, how big, how episodic, and how much the mantle still moves beneath the crust. If you want a calm, continuous picture, imagine Venus as a slow-breathing interior under a rigid shell, with mantle plumes rising like slow heat bubbles, lifting the crust into domes, cracking it into rings and fractures, letting lava seep and spread, then cooling and settling, repeating over millions of years. On Earth, you'd see it as a violent eruption or an earthquake. On Venus, it's too slow and too hidden to feel dramatic in the moment. It's like geological motion happening behind a curtain. And that curtain is always there, the bright cloud deck above, reflecting sunlight and hiding everything, turning the planet into a smooth, glowing object in our sky, while the surface below holds ridges, plains, and volcanic scars in perpetual dim light. Let that contrast do the calming work. The surface is real but unseen, mapped by invisible waves, reshaped by slow internal forces, covered by a thick atmospheric ocean, and above it all the clouds circle endlessly, steady and repeating, until your own thoughts stop trying to see everything clearly and simply accept the quiet unknown. Venus's atmosphere isn't just thick, it's a full-body environment that rewrites every normal instinct you have about air, weather, and sky. Because on Earth the atmosphere feels like a thin layer you move through. But on Venus the atmosphere is the main event, a massive CO2 ocean pressing down on rock, layered with chemistry, driven by sunlight, and moving in patterns that make the planet feel like it has two speeds at once, the surface locked in slow, heaviness, and the cloud tops racing like a planet-wide conveyor belt. The composition is simple in headline form, mostly carbon dioxide, with nitrogen as a smaller component, but the behavior is anything but simple, because the thickness changes how energy moves. In a thin atmosphere, heat can radiate out, and the air can be patchy. In a thick atmosphere, heat is stored, transported, and redistributed efficiently. Venus doesn't cool off at night the way a thin world would, and it doesn't have sharp weather boundaries the way Earth does. The planet is basically wrapped in insulation so strong that the surface temperature stays extreme across latitudes and across day-night cycles, and even though Venus rotates slowly, the atmosphere smooths out what would otherwise be huge differences. This is why Venus can be unimaginably hot without needing constant direct sunlight at every point. The atmosphere acts like a thermal flywheel, holding and sharing energy. But the part that makes Venus feel most alien is the vertical structure. If you slice Venus's atmosphere into layers, you get different worlds stacked on top of each other. Near the top, above the main cloud deck, the conditions are more moderate by comparison, and you can find regions where pressure and temperature aren't instantly destructive. Then you descend into the cloud layers, and everything becomes chemistry. Sulfuric acid droplets, sulfur dioxide, trace compounds, photochemical reactions driven by ultraviolet light, and an endless haze that blurs the sun into a diffuse glow. Keep descending, and the air gets denser and hotter until it becomes that crushing, furnace-like lower atmosphere that hugs the surface. Venus is a planet where the sky is not one place. It's a gradient of worlds, each with its own physics. The cloud deck is where Venus shows its personality from space. The clouds are highly reflective, which is why Venus shines so bright in our sky, but reflective doesn't mean harmless. It means the planet is wrapped in a bright shroud that both hides the surface and participates in the energy balance. The clouds are mainly sulfuric acid aerosols, tiny droplets suspended in the atmosphere, forming multiple cloud layers. They're produced through a chain of reactions involving sulfur dioxide and water traces under sunlight. The details can get technical fast, but the feeling is simple. Venus has an active chemical factory in its sky. Sunlight hits sulfur compounds, reactions create acids, droplets form, droplets scatter light, and the cloud deck renews itself. And because the clouds reflect a lot of incoming sunlight, people sometimes assume they should cool the planet, but the greenhouse effect below is so overwhelming that the planet remains extremely hot anyway. It's like wearing a white coat in an oven. You reflect some radiation, but you're still inside the oven. The greenhouse trapping in the thick CO2 atmosphere dominates the final surface. Temperature, because outgoing infrared radiation from the hot surface is absorbed and re-emitted downward, and the lower atmosphere's density makes it extremely hard for heat to escape. The lower atmosphere is where the weight feeling comes from. Pressure at the surface is so high that it's useful to stop thinking of it as air and start thinking of it as a compressible fluid. If you imagine being deep underwater, that's the closest everyday analogy. Not because Venus is wet, but because pressure is the same kind of concept. Force from the mass above you. On Venus, the mass above you is gas, and because it's hot, that gas is energetic, meaning the lower atmosphere is a thick, hot reservoir that doesn't want to change quickly. That stability is why Venus can feel calm in a strange way. It's hostile, but it's steady. The planet isn't constantly flipping between states. It's locked. Now layer in the winds, because Venus's winds are where the planet's two-speed nature becomes most obvious. At the surface, winds are not necessarily the insane hurricane-like chaos people imagine, because dense air doesn't need high speed to move momentum, and friction with the ground and the slow rotation change the near-surface circulation. But high above, near the cloud tops, the atmosphere super-rotates, circling the planet far faster than the solid body rotates. This is one of those facts that feels wrong until you remember that an atmosphere can exchange momentum internally and with solar heating. Superrotation likely involves a combination of global circulation cells, wave transport of momentum, and thermal tides, planet-scale atmospheric waves driven by periodic heating patterns. The result is that the cloud layer becomes a fast-moving ring around the planet. If you were floating at cloud-top altitude, you'd experience a world that moves quickly, where the view shifts and the winds rush around you, while the planet beneath you barely turns. It's like standing above a slow carousel while the air around you is on a moving walkway. And because the clouds are opaque, most of the visible weather is confined to the cloud patterns themselves. Bright streaks, darker bands, swirling structures seen in ultraviolet imaging that reveal variations in absorption and chemistry. Venus's cloud patterns are not just pretty. They're evidence of dynamic circulation, of mixing, of chemistry changing with sunlight exposure and possibly of episodic injections of gases from below. This brings up another deep Venus question. How much is Venus still outgassing today? Sulfur dioxide levels, for example, are interesting because SO2 can be consumed in the upper atmosphere by chemical processes, so maintaining certain levels could imply resupply, potentially volcanic. Observations over time have hinted at variability that could be explained by volcanic activity, but the cloud environment makes definitive answers hard. Still, Venus doesn't need confirmed right-now eruptions to feel active as a system. The atmosphere itself is active, constantly processing sunlight into chemistry, constantly moving as a global engine, constantly maintaining an extreme greenhouse state. It is a living circulation pattern, even if the surface is still. The upper atmosphere interacts with the solar wind, too. Venus lacks a strong intrinsic magnetic field like Earth's, so the solar wind can interact more directly with the upper atmosphere, inducing magnetic effects and stripping some particles over time. This matters for long-term evolution because atmospheric loss, especially of lighter elements, can change a planet's trajectory. If Venus once had more water, hydrogen could escape to space after water molecules are broken apart by ultraviolet radiation, leaving the planet drier and locking it into a CO2-dominated state. The atmosphere you see today is not just a snapshot. It's an outcome. It represents what remains after billions of years of balance between outgassing, chemical processing, and escape. Another layer that makes Venus fascinating is how its slow rotation shapes circulation. On Earth, fast rotation helps organize weather into familiar patterns: jet streams, trade winds, cyclones. On Venus, rotation is slow, and the atmosphere is thick, and the result is a circulation regime that doesn't match Earth's mental template. Venus likely has large-scale circulation cells that transport heat from equator to poles, contributing to that uniform temperature distribution. And because the atmosphere is so thick, even modest winds can transport significant heat and momentum. The planet doesn't need fast surface winds to be efficient. It needs mass. Venus has mass in its atmosphere. If you zoom out, Venus's atmosphere becomes an example of how stable extreme climates can be. People often frame Venus as a warning, but the more accurate framing is that Venus shows how a climate can become trapped in a stable attractor state. Once you lose water and once CO2 becomes dominant, you remove the main sinks that could lower greenhouse gases, and the system becomes self-maintaining. The temperature is high, which prevents water from condensing, which prevents water-based weathering, which prevents CO2 drawdown, so the CO2 stays, so the temperature stays high. That's not a moral story, it's a system story. Venus is a locked loop, and that loop also shapes surface atmosphere chemistry. In an environment of high temperature and pressure with CO2 dominance, certain minerals and surface reactions can change the atmospheric composition at trace levels, and the atmosphere can alter the surface through corrosion and chemical weathering. So even without rain, Venus has a form of weathering, just driven by heat and reactive gases rather than by liquid water. That means the boundary between air and rock is more interactive than you'd expect from a dry planet. Venus can still have surface chemistry as a slow exchange. For sleep narration, the cleanest way to feel Venus's atmosphere is to picture descent. Start above the clouds, where space is black and the planet is a bright, curved horizon. Then sink into the upper haze where sunlight becomes milky and scattered, where cloud features swirl past you like pale rivers. Deeper, you enter the cloud deck, an endless luminous fog of acid droplets that diffuses everything into soft light. There's no clear sun, only brightness. You pass through layers where chemistry changes with altitude, where droplets form and fall and evaporate again in a cycle, where sulfur compounds rise and get processed. Deeper still, you drop below the clouds into a darker, denser world. The light grows dimmer, but still warm-toned. The air becomes heavier. Temperature climbs steadily. You feel pressure increasing like the slow squeeze of a giant hand. Finally, you reach the lower atmosphere where the planet becomes a furnace sealed under a lid of gas. The ground beneath is rock, volcanic plains, ridges, scattered stones, under a sky that never clears. Everything is quiet not because nothing happens, but because everything happens slowly and steadily. The atmosphere above you is a massive machine, circulating and processing sunlight and chemistry, holding heat the way a deep ocean holds warmth, indifferent to day or night. And above that, far up where the winds race, the clouds continue their fast loop around the planet, repeating and repeating, a motion so consistent it becomes hypnotic. Venus is the planet of permanence, a thick sky that never opens, a surface that never cools, clouds that never part, and cycles that run without drama, just persistence. If you let that image sit, your mind stops trying to force excitement out of it. Venus doesn't need excitement. Venus is a slow, sealed engine, and the more you accept its steady rhythm, clouds circling, chemistry turning, heat trapped, the easier it becomes to let your own thoughts do the same thing. Slow down, loop gently, and finally fade out. Venus has a reputation that's way too simple. Earth's twin turned hell, and that's lazy because it skips the interesting part, which is how Venus keeps its secrets. It's right there, bright in the sky, closer than Mars, similar in size to Earth, and still it's one of the hardest planets to truly know, because its atmosphere doesn't just cover the surface, it erases it from view, and when a world hides itself that completely, you're forced to understand it through patterns. Patterns in chemistry, patterns in heat flow, patterns in winds, and patterns in the way the surface responds even when you can't watch it directly. That's why Venus stories feel like drifting through fog. You can't grab the planet by the edges. You have to let it form in your mind in layers. One of the calmest ways to approach Venus is to start from the top and move down, because Venus is a planet where altitude changes everything. High above the cloud tops, Venus is almost elegant. It's a bright curve with a soft atmosphere, a smooth white-yellow sphere reflecting sunlight. You could look down and see swirling cloud patterns, bands, waves, motion that looks like weather. But that motion is mostly in the clouds. The surface is still hidden. The top layer is where the planet seems approachable. Temperatures can be less extreme, pressures can be closer to what we consider survivable, and the sunlight is intense. This is the altitude where people daydream about floating cities, because the idea isn't completely insane in principle. There's a range of heights where the pressure is closer to Earth sea level, and the temperature is not instantly deadly. But even there, you're floating in an atmosphere that is chemically hostile, because the clouds are sulfuric acid droplets, and the air is still mostly carbon dioxide. It's not habitable. It's simply less instantly destructive. Venus teases you with a narrow band of not impossible, then reminds you it's still Venus. Descend into the cloud deck, and you enter the planet's main identity. Sulfur chemistry and sunlight working like a factory. Sulfur dioxide can rise from lower altitudes and get processed by ultraviolet light. Water traces, sulfur compounds, photochemical reactions, these build sulfuric acid aerosols that condense into droplets. Those droplets form thick layers of clouds that reflect sunlight and hide the surface. And because the cloud deck is so reflective, Venus looks bright from Earth. That brightness is what tricks people into thinking Venus is gentle. It's not, it's just reflective. The clouds are doing two things at once. They bounce sunlight away, which is a cooling effect, but they also create an insulated, layered atmosphere where heat from below struggles to escape. And below the clouds, the greenhouse effect is so dominant that the planet's reflectivity doesn't rescue it. The surface remains extremely hot. Think of the clouds as a bright lid. The lid reflects some energy, but the pot underneath is still boiling because the heat can't get out. The lower atmosphere is the real cage. This is where CO2 dominates and pressure becomes crushing. The deeper you go, the more the air stops feeling like air and starts feeling like a weight. It's dense. It holds heat. It transports heat. It makes the planet uniform in temperature across day and night, because the atmosphere is too thick to allow the surface to radiate away heat quickly. Even with Venus's slow rotation, you don't get dramatic cooling at night. The planet is locked into a constant state. The greenhouse effect is not an event. It's the planet's equilibrium. And Venus's equilibrium is extreme. CO2 absorbs infrared radiation. The surface radiates heat. CO2 traps it. The heat comes back down. The lower atmosphere warms and becomes even better at storing energy. This repeats until the whole system settles into a temperature so high that liquid water can't exist at the surface, and that fact alone keeps the lock-in permanent, because without liquid water, you don't have Earth-style carbon sinks. Earth can hide CO2 in oceans, in rocks, in carbonates, through weathering and biology. Venus can't, at least not in the same way now. So CO2 stays. And when CO2 stays, heat stays. That's the loop. Venus is an example of a climate state that stabilizes itself by removing the exit routes. The story of how it got there is one of the most important what-if stories in planetary science, because Venus may not have started like this. Early Venus could have had more water. It could have had conditions closer to Earth's. But being closer to the Sun means more heating. More heating means more water vapor. Water vapor is a greenhouse gas, so it amplifies heating. That feedback can run away. If the oceans evaporate and the atmosphere becomes saturated with water vapor, ultraviolet light can break water molecules apart in the upper atmosphere. Hydrogen escapes to space. Oxygen reacts with rocks. Over time, the planet loses its water. And once water is gone, the carbon cycle collapses. Volcanic outgassing continues. CO2 accumulates, the greenhouse strengthens, and the planet becomes what it is today: dry, sealed, and hot. Venus is the planet where slightly different starting conditions might lead to a completely different ending. Not because it's random, but because feedback loops create attractor states. Once you fall into one, it's hard to climb out. Venus's winds add another layer of hypnosis. The planet rotates slowly and in retrograde, which already makes it feel backwards, but the atmosphere does its own thing. At the cloud tops, superrotation whips the atmosphere around the planet in just a few days, far faster than the planet's surface rotates. So you have this surreal situation where the ground is crawling and the sky is sprinting. The reasons involve global circulation, wave-driven momentum transport, thermal tides, and the way heating patterns push energy into the flow, but you don't need the math to feel the effect. Venus's clouds are constantly circling, constantly moving, constantly maintaining a fast loop above a world that barely turns. If you were suspended in those clouds, you'd feel the planet racing underneath you, even though the planet itself is slow. And because the cloud deck is so thick, most of Venus's visible weather exists in that upper layer. The swirling patterns you see in ultraviolet images aren't water storms. They're chemical and thermal patterns, variations in absorption, composition, and cloud thickness. It's weather without rain, motion without clear sky, storms without oceans. That's Venus. Then there's the surface itself, which stays hidden unless you use radar. Radar maps show a world that seems to have been paved by volcanism. Vast plains, large volcano-like structures, ridges and rifts. Corona, huge circular features thought to be created by mantle plumes lifting the crust and fracturing it. Venus doesn't show the neat global plate tectonic system Earth has. Instead, it may operate with a stagnant lid, and if that's true, it changes everything about how heat escapes. Earth vents heat constantly along plate boundaries. Venus, with a stagnant lid, might store heat until it releases it in episodes, resurfacing large areas and resetting crater records. This fits the crater count puzzle. Venus doesn't have as many craters as a dead ancient surface should. The surface seems relatively young and globally similar in crater distribution, which suggests a resurfacing event or series of events. That means Venus could be geologically restless, even if it's not obviously active in the moment. The planet could be quiet now, but not dead. Volcanism also connects back to the atmosphere, because volcanic gases include CO2 and sulfur compounds. Sulfur dioxide in the atmosphere can be consumed by chemistry at higher altitudes, so if you see variability in SO2, one possible explanation is variable volcanic supply. Observations have hinted at changes, but Venus is difficult, and that's the theme again. Everything is possible, but hard to confirm. The clouds hide the surface. The conditions destroy long-lived hardware. The signals are indirect, so Venus remains a planet of inference. And that makes it perfect for a sleep story because your brain can relax into the uncertainty. You don't need crisp answers to drift. You just need a coherent scene. So picture Venus as a dim orange world under a ceiling of thick clouds. The light at the surface is muted, shadows soft, the horizon close because the dense atmosphere swallows distance. The air presses down like a deep ocean. The ground is volcanic rock, dark plains, scattered stones, ridges rising gently in the distance. Somewhere far above, the cloud tops whip around the planet at high speed, but down here the surface is steady, almost still, as if the planet is holding its breath. And over everything is the sense of permanence. Venus doesn't shift quickly. It doesn't cool. It doesn't clear. It cycles in slow, stable extremes. It's a planet that found a climate state and got stuck there. And the more you sit with that idea, the slow, sealed engine of CO2, clouds, chemistry, and heat, the more your own thoughts start to lose their urgency, because Venus doesn't reward urgency. Venus rewards patience. It's been bright in our sky for as long as humans have watched, shining calmly as a morning or evening star, and behind that calm light is a world that runs on slow physics, repeating circulation, and steady heat. Let that steadiness be the rhythm in your mind. Clouds circling, chemistry turning, pressure holding, heat trapped, surface silent. Repeat it. Drift with it. And let the bright star in the sky become what it really is in your imagination. An endless cloud-wrapped world turning slowly in quiet. Venus is the planet that looks like a calm, bright star from far away and then turns into a sealed pressure chamber the moment you actually imagine standing on it. Because everything about Venus is a lesson in how a world can hide behind layers and still be intensely active in the ways that matter. It's almost Earth's twin in size and mass, close enough to feel familiar, yet it ends up as a totally different outcome because the chain of climate feedbacks on Venus didn't just warm the planet, it locked it into a permanent extreme state, and once that lock clicks shut, it becomes unbelievably hard to undo. The core reality is the atmosphere, mostly carbon dioxide, extremely thick, with a surface pressure so high it's easier to think of it like being deep underwater, except the water is hot gas, and it never stops pressing down. CO2 is excellent at absorbing infrared radiation, which is the heat a warm surface tries to radiate back into space. So the more CO2 you have, the more outgoing heat gets caught, re-emitted, and sent back down over and over, and Venus takes that effect to the maximum. The lower atmosphere becomes a massive heat reservoir that barely changes, and because it's so dense, it transports heat efficiently, smoothing out temperature differences across day and night and across latitudes. So Venus doesn't need dramatic sunlight swings to stay hot everywhere. It stays hot because the atmosphere is a thermal flywheel. The cloud deck is the planet's mask. Thick layers of sulfuric acid droplets suspended in the atmosphere, bright and reflective, making Venus shine brilliantly in our sky as the morning star or evening star. But those clouds aren't a soft blanket. They are a chemical factory built from sulfur compounds processed by sunlight. And they are also a visual wall that blocks normal light from reaching the ground, so the surface is hidden continuously. That's why Venus became a planet we had to decode rather than simply photograph. Radar mapping, spectroscopy, brief lander transmissions, because visible cameras just see clouds. And once radar gave us the shape of the surface, Venus stopped being featureless and started looking like a world that has been repaved. Vast volcanic plains, large volcano-like constructs, long rift zones, ridges, fracture networks, and especially corona. Giant ring-shaped or oval tectonic features thought to be produced when mantle plumes rise, push the crust upward, crack it into concentric patterns, then evolve and sometimes collapse, leaving a signature that doesn't match Earth's plate boundaries but still screams interior motion. Venus doesn't appear to have Earth-style global plate tectonics recycling crust in neatly moving pieces, which matters because plate tectonics is one of Earth's most effective heat release and carbon cycling tools, and if Venus operates more like a stagnant lid planet, one large crustal shell that doesn't break into long-lived moving plates, then internal heat has fewer steady escape routes, meaning heat can build under the lid until it's released through episodic volcanism and tectonic deformation, potentially resurfacing large areas. That idea fits the crater puzzle. Venus has impact craters, but not the massive crater saturation you'd expect from a dead ancient surface, and many craters look relatively fresh and evenly distributed, hinting that the surface may have been globally or regionally renewed on geologically recent timescales, burying older craters under lava flows and tectonic reshaping. The absence of liquid water on the surface today changes the whole look and feel, too. No rivers carving valleys, no rain-driven erosion, no oceans regulating gases. So Venus's landscapes are sculpted mainly by volcanism, tectonics, and chemical, weathering driven by hot CO2 and sulfur chemistry rather than by water cycles. Even weathering on Venus isn't the Earth kind. It's chemical alteration under extreme heat and pressure, potentially forming coatings that can change radar reflectivity, and some high-elevation regions appear unusually radar bright, which has fueled ideas about mineral deposits or chemical frosts that could be stable only at those slightly cooler, lower-pressure highlands. Not snow, but a similar concept of selective stability by altitude. The sky dynamics are just as alien because Venus rotates slowly and in retrograde compared to most planets, so the Sun's apparent motion would feel backwards and the passage of a day would feel stretched. Yet above that slow-turning ground, the atmosphere super-rotates, with cloud-top winds racing around the planet in just a few days, meaning the sky is the fast-moving part and the surface is the slow part. This super-rotation is driven by global circulation and wave processes that transport momentum, thermal tides, planetary waves, and the way sunlight heats different regions of the atmosphere. So the atmosphere becomes a planet-scale engine that sustains its own rapid motion. And because the clouds are opaque, much of what we call Venus weather is seen in those cloud patterns. Bands, swirls, wave-like streaks revealed especially in ultraviolet imaging, where chemical absorbers create contrast. So it's a world of motion without blue sky, storms without water, and circulation driven by heat and chemistry rather than by oceans and evaporation. The long-term climate story that likely created today's Venus is where the planet turns into a systems lesson. If early Venus had substantial water, being closer to the Sun would raise temperatures, increasing water vapor in the atmosphere, and water vapor is itself a greenhouse gas. So more vapor means more heat. More heat means more vapor, forming a feedback loop that can run away until oceans evaporate. Once water reaches the upper atmosphere as vapor, ultraviolet light can break it apart, hydrogen can escape to space, and over long time the planet loses water permanently. Losing water is losing a thermostat, because liquid water enables strong carbon sinks through dissolution, weathering, and mineral formation. And without those sinks, CO2 outgassed by volcanism accumulates. Once CO2 dominates, the greenhouse becomes extreme. Once the greenhouse is extreme, liquid water can't return. And without liquid water, you can't easily draw down CO2, so the planet gets stuck in a stable extreme attractor state, where the very conditions needed to cool the planet are the ones the planet has removed. The cloud deck complicates the story in a way that's soothing rather than confusing if you hold it correctly. Clouds reflect sunlight, which is a cooling effect, and Venus's clouds are very reflective. Yet the greenhouse below is so strong that reflection doesn't rescue the surface. It just means the top of the atmosphere can be cooler, while the lower atmosphere remains a furnace. It's like a bright lid on an oven. Some energy bounces away, but what gets in can't get out from the bottom, so the surface stays blistering. The chemical cycle of sulfur also ties atmosphere to geology, because sulfur dioxide can be supplied by volcanic outgassing and then processed in the upper atmosphere into sulfuric acid aerosols, meaning the cloud chemistry may be sensitive to what the interior is doing, and there have been observations over time suggesting variability in certain atmospheric compounds that could be consistent with episodic injections from below, although Venus is difficult enough that definitive proof is hard. That difficulty is the constant theme. Venus is close, but it's hostile to hardware, and it hides behind clouds, so we're always inferring from partial signals. Radar shapes, spectral lines, probe measurements, brief surface images captured in short lander lifetimes before heat and pressure overwhelm electronics. Those surface images, when they exist, don't look like fire or chaos. They look like dim stillness. Rocks scattered on a plain, a low-contrast horizon, muted yellow-orange light filtered through thick air. Soft shadows, because sunlight is diffused by the cloud layers, and a sense that the atmosphere is not a backdrop, but a physical presence. The calm way to visualize Venus is to stop imagining it as dramatic and start imagining it as heavy. A world with a ceiling of clouds that never parts, where the sky is always overcast, where distance fades quickly, where the air is thick enough to feel like you're inside something, not outside, and where the temperature never really changes because the planet is sealed into its own greenhouse equilibrium. Then let the layered structure settle in your mind like a slow descent. High above, bright cloud tops and rapid winds circling the globe in super-rotation. Deeper, a luminous acid fog where chemistry is constantly being made and remade by sunlight. Lower still, the thick CO2 ocean where heat is stored and shared so efficiently that time of day stops meaning much. And at the bottom, volcanic rock plains and ridges mapped by radar, shaped by mantle forces that push and crack the crust into rifts, ridges, and coronae, and perhaps resurfaced in episodic outbursts when internal heat finally finds an escape. Venus becomes a planet of permanence and repetition. Clouds circulating, chemistry cycling, heat trapped, pressure holding steady, geology expressing itself through slow deformation and long-term resurfacing rather than through familiar plate boundaries, and the entire world maintaining a stable extreme state for long spans of time. And that's why Venus is perfect for sleep narration when you strip away the clichés. It doesn't need jump scares, it needs rhythm because Venus is all rhythm, super-rotating clouds, looping endlessly above a slow-turning surface, a greenhouse effect continuously recycling heat, chemical aerosols continuously forming and settling and reforming, and an interior continuously circulating beneath a crust that responds not in quick quakes you would notice moment to moment, but in long-term patterns etched into the ground. If you let your thoughts follow those loops, clouds around, heat down and back, chemistry up and down, mantle rising and sinking, you stop searching for a climax because Venus doesn't offer one. It offers a steady closed system, a bright masked world that stays the same in the ways that matter, and the more you accept that steadiness, the easier it is to let your mind do the same thing. Slow down, repeat gently, lose sharp edges, and fade into quiet. Venus also has this weird power where it makes you realize how much of a planet is actually the story of what it can keep and what it loses, because Venus didn't just become hot, it became trapped in a state where the things that would normally pull it back, water, carbon sinks, cycling, either disappeared or stopped working. And once that happens, the planet stops being flexible and starts being stubborn. The simplest way to hold Venus in your mind is as a closed loop. CO2 dominates. CO2 traps heat. Heat prevents liquid water. No liquid water means no strong long-term CO2 removal. CO2 stays dominant, and the loop reinforces itself. So Venus becomes a stable extreme equilibrium rather than a world that fluctuates. That stability is why Venus can feel strangely calm in a narration, even though the numbers are violent, because it's not chaotic, it's consistent, like an environment that has already finished changing and now just maintains itself. You can think of Venus's atmosphere as having weight and memory. Weight because the pressure at the surface is crushing, and memory because thick atmospheres store heat and smooth out variability, so the planet doesn't respond quickly to day-night changes. It just holds on to the same thermal state. The greenhouse on Venus is so strong that even if you tried to imagine a cold night, you can't really create one. Any heat that tries to leave gets absorbed and sent back down, and the dense lower atmosphere carries energy around, so the whole surface stays baked and uniform. The cloud deck above is bright and reflective, making Venus luminous from Earth. But that reflectivity mostly affects the upper energy balance, while the deep atmosphere below controls the surface. So the white shining Venus you see in the sky is basically the planet's reflective mask, a smooth glowing lid over a furnace. And because the clouds are sulfuric acid aerosols, Venus's sky becomes chemistry you can almost picture as a slow fog machine. Sulfur dioxide rises, sunlight processes it, sulfuric acid droplets form, droplets persist as cloud layers, droplets fall and evaporate lower down, and the cycle repeats, creating a permanent veil that both hides the surface and defines the planet's appearance. Within that veil, the atmosphere moves in patterns that are hypnotic because they're planet-scale and repetitive. Superrotation at the cloud tops loops around the globe every few days, and cloud patterns reveal waves and streaks and swirling bands, not because Venus has Earth-like storms with rain, but because heating and chemistry create contrasts, and because global circulation organizes the clouds into repeating structures. The slow retrograde rotation of the planet underneath adds to the dreamlike effect because it breaks your instinct for time and direction. Venus spins slowly and backwards, so sunrises and sunsets would be stretched and strange. Yet the cloud layer ignores that slowness and races on its own schedule, meaning Venus is a world where the sky moves faster than the ground, like the planet is wearing a fast-moving cloak. The surface beneath that cloak is mostly revealed by radar, and radar makes Venus feel like a planet read through touch rather than sight, because you're sensing shape, roughness, and reflectivity indirectly. What radar shows is a landscape that looks dominated by volcanism and tectonic deformation. Broad basaltic plains, lava-like flow fields, large volcano constructs, rift zones where the crust appears pulled apart, ridge belts where it appears compressed, and those huge corona that look like circular or oval tectonic scars, likely formed by mantle plumes pushing upward and fracturing the crust in rings. Venus's lack of clear global plate tectonics makes those features feel more like the crust is one large shell responding locally to mantle upwellings rather than a mosaic of moving plates. And if the crust is a stagnant lid, the planet's interior heat has fewer steady exits, which can lead to a different style of planetary cooling. Heat builds under the lid, stress accumulates, and then large volcanic episodes. can release that heat and resurface vast areas, burying older craters and resetting the surface age in a way that produces the crater distribution we see. Enough craters to show it's been bombarded, but not enough to look ancient and saturated. This episodic resurfacing picture is calming in a sleep narrative because it's slow and cyclical, like the planet spends long periods storing energy and then rewrites itself in broad strokes over millions of years. Then settles again, with no fast changes in human time. And because Venus has no liquid water at the surface today, the usual Earth sculpting processes are missing. No rivers carving, no rainfall smoothing, no oceans dissolving gases. So Venus's landscapes are preserved in a different way, not polished by water, but altered by heat and chemistry. And that's why some highlands appear unusually radar bright, possibly due to mineral coatings that form under the specific temperature-pressure chemical conditions at high elevations, like a selective deposit that only stabilizes in those zones, a kind of chemical snow line without snow. The long-term evolution story ties surface and sky into one locked narrative. If early Venus had more water, increased sunlight could have driven more evaporation, water vapor greenhouse feedback could have intensified warming, and over time, ultraviolet light could have broken apart water in the upper atmosphere, allowing hydrogen to escape to space, slowly drying the planet. Once water is gone, the strong carbon sinks vanish, and volcanic outgassing of CO2 accumulates in the atmosphere, strengthening the greenhouse until the surface is too hot for water to return, which prevents the sinks from restarting, which keeps CO2 high, so the planet falls into a stable extreme loop. Even the idea of modern volcanism on Venus becomes part of the atmosphere story, because sulfur compounds in the atmosphere can be consumed chemically, so maintaining them could require resupply, and while direct confirmation is difficult, the possibility reinforces the sense that Venus is not simply frozen in time, it is actively maintaining its atmospheric chemistry and thermal state through ongoing processes. The most important sleep-friendly feeling in all of this is enclosure. Venus doesn't feel open. It feels enclosed, like you're inside a world rather than on the surface of one, because the clouds form a permanent ceiling and the dense atmosphere makes the horizon feel close, and the light at the surface would be diffuse and warm-toned, with soft shadows and low contrast, like being underwater in a hazy amber sea. Except the sea is air, and the floor is volcanic rock. Above that floor, the atmosphere presses down and holds heat, and above that, the clouds circle endlessly in their own fast loop, and far above that, Venus shines in space as a bright white curve that looks peaceful because the violence is hidden in the physics underneath. If you let those layers stack in your mind, bright lid, chemical fog, dense heat reservoir, silent rock plains, you get a stable repeating image that doesn't demand attention, it simply persists, and that persistence is what quiets your brain. Venus is a world that stays in its state, that repeats its cycles, that maintains its loops, and the more you follow those loops, CO2 trapping, cloud cycling, super-rotation, slow geology, the more your thoughts stop trying to jump around and start moving in the same slow circular way until they finally settle and fade. Venus can also be understood as a planet that runs on vertical motion more than horizontal variety, because the surface itself doesn't offer the kind of changing scenery Earth does. No oceans, no forests, no weather fronts you can watch rolling in. Yet the atmosphere above is layered into distinct regimes, and each altitude band behaves like its own world. So the calm way to keep Venus interesting without getting noisy is to keep returning to that idea of stacked environments. At the top, sunlight is sharp, space is black, and the planet's curve is bright. At mid-levels, the clouds become a thick, milky haze where chemistry lives. Lower down, the air becomes a dense thermal reservoir. And at the bottom, the surface sits under that weight, steady and dim, like a floor under an endless ceiling. This is why Venus feels like an enclosed system, because most of what happens is trapped within layers, circulating internally, repeating rather than venting outward. The planet's brightness from Earth is almost like a constant reminder of that enclosure, because it's not the surface shining, it's the cloud lid reflecting sunlight, and the same lid that makes Venus beautiful in the sky is the lid that blocks your view of everything underneath, forcing you to trust indirect evidence. The indirect evidence is what gives Venus its dreamlike quality. Radar revealing plains and ridges you can't see with your eyes. Spectroscopy revealing gases you can't smell. Probes measuring pressure and temperature in a place you can't survive. So the planet becomes a world you experience through instruments the way you experience a dream, through scattered images. Fragments that imply a whole. One fragment is the idea of a soft surface horizon, because the thick atmosphere and diffuse light would make distance fade. Another fragment is the sense that Venus's surface is made mostly of volcanic rock, because the plains look like basaltic flows and the lander images show rocky terrain. Another fragment is the sense that the interior still matters, because coronae and rifts suggest mantle upwellings and crustal stress. Another fragment is the atmosphere's chemical loop, because sulfuric acid droplets form and cycle, and trace sulfur compounds hint at ongoing supply. None of these fragments alone is a complete story, but together they build a planet that is consistent, a world where the main motion is the sky, and the main permanence is the heat. The heat is the anchor of Venus's identity, because once you have a massive CO2 atmosphere, the surface becomes the heat source, and the atmosphere becomes the trap. And the trap makes the surface hotter, and the hotter surface radiates more, and the trap catches more, until the system settles into a stable, high-temperature state. That stability makes Venus feel almost hypnotic, because it's not changing weather. It's constant climate, a steady set of conditions that persist. And inside that steady climate, the atmosphere still has structure. Superrotation at cloud tops, slower winds lower down, circulation cells moving air from equator to poles and back, waves traveling through the cloud deck, all of it repeating. The superrotation is especially soothing as an image because it's like a loop you can set your thoughts to. The cloud layer circles, 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 carrying patterns around the planet, while the surface below barely turns. If you want to picture time on Venus, picture it as two clocks, a slow clock for the ground and a fast clock for the clouds, and neither clock is frantic, they're just different. The fast one is steady motion, the slow one is near stillness, and both are continuous. The geology has that same feeling of continuity, because even if Venus experiences episodic resurfacing, those episodes are still slow on human scales. Planetary scale lava flooding and crustal deformation unfolding over long periods, not sudden explosions you'd watch from a window. Venus might store heat under a stagnant lid and then release it in broad volcanic renewal, then settle, and the surface you see today could be the result of that kind of cycle, which is why crater counts don't match an ancient untouched surface. And because water-driven erosion is absent, the surface retains its volcanic character, not carved into river valleys, but shaped by flows, ridges, rifts, and fracture patterns. Even the idea that highlands might have radar-bright coatings fits the layered system theme. Small changes in altitude slightly change temperature and chemical environment, and those slight changes can allow different minerals or coatings to form, so Venus still has zones, just not the lush zones Earth has, but chemical zones. The long-term history loops back again to water loss, because if Venus once had more water, runaway greenhouse and hydrogen escape could have dried it out, leaving CO2 behind and locking the climate. And once locked, the planet becomes a stable end state, a dry CO2 world with sulfuric acid clouds, super-rotating winds, and a hot surface under crushing pressure. For sleep narration, the point isn't to scare, it's to emphasize the steady repetition. the cloud lid reflecting sunlight, the chemistry renewing the clouds, the winds circling the globe, the heat trapped below, the surface hidden but mapped by radar, the mantle still moving under the crust, the planet rotating slowly in retrograde while its sky races ahead, and through it all Venus shining calmly in our sky as if none of it is happening, as if it's just a bright, quiet star. Let that contrast settle, beautiful from afar, heavy up close, constant always, and let your thoughts follow the easiest rhythm Venus offers. Slow descent through layers, then endless circling above, repeating until everything in your head becomes as soft and diffuse as the light under Venus's clouds. Venus is also where you can stop thinking about places and start thinking about conditions, because on Venus the same location can feel like a different world depending on altitude and chemistry, and the planet's most important geography is the vertical gradient rather than the map of continents. That's why the idea of floating in Venus's upper atmosphere keeps coming back in science fiction and serious discussion. It's one of the few ways the word nearby feels meaningful on Venus, because the surface is not a place humans can occupy, but certain layers of the atmosphere can be closer to familiar pressures and temperatures, even if the chemistry remains hostile. And this makes Venus feel like a planet that is almost negotiable but never truly welcoming, like it offers you a narrow band of less impossible inside an otherwise sealed furnace, a reminder that planetary environments aren't binary, they're stratified. But even if you ignore the floating city daydreams, that stratification is still the cleanest way to understand how Venus works. The upper atmosphere is where sunlight drives photochemistry and where the cloud patterns show dynamic motion. The cloud deck is where sulfuric acid aerosols form and persist, reflecting light and hiding the ground. The lower atmosphere is where CO2 dominates the radiative physics and where pressure and density create a deep heat reservoir. And the surface is where all of that energy lands, trapped, steady, and extreme. The planet's biggest feature is not a mountain or a crater, it's the atmospheric mass itself, because that mass creates the pressure that changes everything, and that pressure makes the planet feel less like a rocky sphere with a thin skin of air, and more like a rock buried under a thick medium. In that medium, sound would travel differently, convection behaves differently, and even the simple idea of wind changes, because dense air can move enormous momentum, without needing hurricane speeds, and the frictional boundary layer near the ground operates under conditions we don't experience on Earth. Yet above, at cloud level, the winds are fast, and that speed difference is one of Venus's signature contradictions. The planet rotates slowly and retrograde, but the atmosphere super-rotates, circling the globe on its own schedule, meaning Venus's weather is like a belt that keeps moving even when the wheel beneath turns slowly. This is where Venus starts to feel like a machine rather than a scene. Inputs are sunlight and internal heat. Processes are greenhouse trapping, circulation, photochemistry, cloud formation. Outputs are infrared radiation, escaping mostly from higher altitudes and slow loss of light gases over time. The machine hums steadily, and because it's steady, Venus becomes predictable in its extremity. The predictability is what makes it oddly calming once you stop insisting it should behave like Earth, the surface. Temperature stays high because the greenhouse effect is strong and constant. The atmosphere stays thick because there's no easy sink for CO2 once water-based cycling is gone. The clouds stay present because the sulfur cycle keeps producing aerosols. And the cloud motion stays fast because the circulation maintains superrotation. Everything is a loop, and loops are soothing when they're not threatening you with sudden change. The planet's surface geology fits the machine framing too, because the surface looks like it has been shaped and reshaped by internal heat, mostly through volcanism, without the continuous plate recycling Earth uses. Radar reveals wide plains that resemble lava flooding, along with huge volcanic constructs and tectonic deformation features like rifts and ridges, and the distinctive corona that suggest mantle upwellings, pushing the crust into circular fracture patterns. That implies the mantle is still convecting beneath a crust that behaves more like on shell, so heat is released through localized plume-related deformation and possibly episodic resurfacing, rather than through global plate boundaries. The crater distribution supports resurfacing because Venus doesn't look like a world that has simply accumulated impacts for billions of years without interruption. Instead, it looks like a world where much of the surface was renewed on a relatively recent geological timescale, burying older craters and leaving a landscape that is broadly similar in crater density across the globe. That global similarity makes Venus feel like it had a reset, which is unsettling in scientific terms because it suggests a planet-wide event or series of events, but in sleep terms it's just another slow cycle. Build heat, release heat, renew surface, repeat. The atmosphere may still be connected to that interior cycle because sulfur compounds in the atmosphere can be consumed chemically, so variations in sulfur dioxide could hint at resupply, potentially volcanic. Definitive confirmation is hard, but the possibility keeps Venus from being a fossil. It becomes an actively maintained system, and maintenance is the right word for Venus because the planet maintains its climate state like a sealed greenhouse that never opens. CO2 traps heat, heat prevents water, lack of water prevents CO2 removal, and so the CO2 stays and the heat stays. If early Venus had water, runaway greenhouse and hydrogen escape could have drained it, leaving behind a drier planet that couldn't restart its cooling mechanisms. And once you accept that history, Venus stops being a mystery of, why is it hot? And becomes a story of, why did it get stuck? Which is more interesting because it's about feedback and thresholds. A small push at the wrong time can tip a system into a different stable state. And Venus is the proof that once a planet crosses a threshold, it can stay on the other side for billions of years. For sleep narration, the most useful way to picture that is as a gradual slide. A slightly warmer early planet increases water vapor increases heat trapping, heat increases vapor, oceans evaporate, water molecules break apart under UV, hydrogen escapes, CO2 accumulates, clouds form, greenhouse intensifies, surface becomes too hot for water to return, sinks vanish, and the planet settles. The settling is the key. Venus has already settled into its extreme state, so you're not waiting for something to happen. You're listening to something that has been happening steadily for a very long time. You can picture Venus at dusk under its clouds, diffuse warm light, no clear sun, a close horizon swallowed by dense air, volcanic rock plains extending into haze, the atmosphere pressing down like a heavy blanket. And far above, hidden from your view, the cloud tops racing around the planet in smooth, continuous superrotation, carrying wave patterns and chemical contrasts in endless loops. And beyond that, from far away, the same planet appears in Earth's sky as a calm, bright point, steady and beautiful, which is the final soothing contradiction. A world that is harsh but quiet, extreme but stable, hidden but bright. Let your mind rest in that stability. The cloud lid, the looping winds, the trapped heat, the unseen surface, and let your thoughts become equally repetitive and soft, circling gently until they fade. Venus is the planet where the word atmosphere stops meaning air around a planet and starts meaning the planet's main body, because once an atmosphere becomes thick enough, it becomes the dominant place where energy is stored and moved, and the rock surface underneath becomes almost secondary, not in importance, but in how much you can experience it. This is why Venus feels like you're always outside looking at a curtain, because the planet's identity is wrapped in clouds that never pull back, and even when you learn the facts, the feeling remains the same. Hidden surface, bright lid, heavy air, steady heat, repeating cycles. And the most calming way to keep talking about Venus without turning it into a lecture is to treat it like a slow set of repeating motions that never end. Clouds circling, chemistry cycling, heat trapped, interior slowly working, surface quietly receiving the load. Venus's cloud deck is not a single layer, but a stacked system. And that matters because layered systems can maintain themselves for a long time. Aerosols form at certain altitudes where chemistry and temperature allow droplet formation. Those droplets can fall and evaporate at lower levels. Gases can rise again. Sunlight can process them again. And the loop keeps producing clouds. So Venus's sky is like a stable factory, constantly making the same product. Those products, acid droplets, reflect sunlight, scatter light, and keep the surface hidden, so the cloud deck becomes the reason Venus looks peaceful, and the reason Venus stays unknowable. The patterns in the clouds that we do see, bands, waves, swirls, are like the only visible handwriting of the planet's circulation. And because the cloud tops super-rotate, those patterns travel around the planet quickly, repeating, looping, forming and reforming. Super-rotation feels like a magic trick because the solid planet rotates slowly, yet the air moves fast. But thick atmospheres can do that because momentum can be transported by waves and tides, and because heating creates global-scale flows that can maintain speed. If you picture it simply, picture a giant conveyor belt of clouds sliding around a slowly turning sphere, endlessly, with no breaks, no clear sky, no sudden changes, just steady circulation. Beneath that fast conveyor belt, the lower atmosphere becomes a dense, hot reservoir. And this is where Venus's greenhouse becomes a physical feeling. CO2 absorbs infrared radiation, holds it, and re-emits it, and in a thick atmosphere the radiation that tries to escape from the surface gets trapped and reprocessed many times before it can finally leave from higher altitudes, so the surface stays hot. The key isn't just that CO2 exists, it's that the amount is so massive that the atmosphere becomes optically thick in infrared, meaning heat can't just radiate out from the ground. Instead, heat is forced to work its way upward through layers, and the deep atmosphere stores and shares it so efficiently that the whole planet becomes thermally uniform. This is why Venus's slow day doesn't create a cool night, because the atmosphere won't allow fast cooling. It's also why weather on Venus is less about changing temperatures and more about circulation and chemistry, movement within a steady climate state. The surface under this atmosphere is not a gentle desert. It's a volcanic rock landscape in dim, diffuse light under crushing pressure. But the important sleep story detail is that it's quiet. No rushing water, no gusting storms like Earth, no seasonal snow, just rock and heat and a ceiling that never opens. We know the surface exists and we know its shape because radar mapped it. Wide plains like lava flooding, giant volcanic constructs, rifts where the crust appears pulled apart, ridges where it appears compressed, and those circular coronas that look like scars from mantle plumes pushing up from below. Those features imply an interior still capable of motion, and because Venus likely lacks Earth-style plate tectonics, the interior's heat may be released in different patterns, localized upwellings and possibly episodic resurfacing rather than steady plate recycling. The crater record supports this because Venus doesn't look like a world that has simply accumulated craters forever. It looks like a world where large parts of the surface were renewed on a geologically recent timescale, smoothing the age distribution, as if the planet pressed a reset button on its own skin. And because there is no surface liquid water to erase, dissolve, and recycle materials the way Earth does, Venus's resurfacing signature is more preserved in volcanic and tectonic features rather than in water-carved landscapes. The absence of water also loops back into the climate lock, because water is one of the strongest long-term regulators for CO2, and if Venus lost water early through runaway greenhouse and hydrogen escape, then it lost the sinks that could pull carbon out of the atmosphere, allowing CO2 to accumulate until the greenhouse became self-maintaining. That is the closed-loop story again. Heat prevents water. Lack of water prevents CO2 removal. CO2 traps. Heat. Repeat. Venus's retrograde rotation adds a gentle disorientation that fits sleep because it breaks your instinct for how planets should move, like the planet is quietly running backward. But the important part is that the atmosphere doesn't care about that direction the way your intuition does. It still circulates, still super-rotates, still runs its chemical factory. The whole planet becomes a set of steady loops operating on different clocks. The slow clock of the surface rotation, the faster clock of cloud-top circulation, the chemical clock of aerosol formation and sunlight-driven reactions, and the geological clock of interior convection and resurfacing episodes. None of these clocks is frantic. They are just persistent, and persistence is what makes Venus feel like an endless environment rather than a series of events. For sleep narration, you can live inside one simple repeating scene. Venus as a bright star in our sky, and behind that bright point, a world under a permanent cloud ceiling, with fast-moving cloud belts above and a dense, hot atmosphere below, pressing down on silent volcanic plains, while the interior slowly pushes and cracks and floods the surface over ages, and the whole system keeps its shape because it's already settled into its stable extreme. If you keep returning to that image, bright lid, looping clouds, trapped heat, hidden rock, your thoughts start behaving the same way Venus's clouds do, circling, smoothing, repeating, losing sharp edges, until there's nothing left to chase and sleep becomes the only natural direction. Venus is also the best place to understand the difference between a planet with weather and a planet with circulation, because Earth's weather feels like constant novelty, storms forming, fronts moving, rain starting and stopping, while Venus feels like a steady global pattern that doesn't care about your need for variety. The planet has circulation, waves, and chemistry, but its climate state is so stable and so locked that the story is repetition rather than change, and repetition is exactly what makes it good for sleep, if you keep it sensory instead of technical. Imagine Venus's cloud layer like a giant looping river of fog, circling the planet endlessly, carrying subtle streaks and waves that you can see only in certain wavelengths because the patterns are chemical contrasts, not fluffy white water clouds. Those patterns exist because sunlight drives photochemistry and because global circulation organizes air into repeating structures, and the fact that the cloud tops super-rotate makes those structures feel like a planet-scale belt that never stops. It's an easy mental metronome, clouds around, while the planet beneath turns slowly and retrograde, quietly moving the wrong way compared to your instinct. Below that belt, the atmosphere thickens into a dense lower layer where the concept of breeze becomes meaningless because dense air can carry power without high speed, and the main thing you would feel is not wind but weight, a constant pressure that makes the environment feel enclosed, and the enclosure is reinforced by light. Sunlight filtered through cloud layers becomes a diffuse warm glow, not sharp brightness, and that diffuse light would make the surface feel close and muted, with soft shadows and a horizon that fades quickly into haze, like being inside a vast amber fog chamber with rock underfoot. The rock itself, from what we know, is largely volcanic. Plains likely made of basaltic lava flows, scattered rocks captured in brief lander images, ridges and rifts mapped by radar, and those massive corona that look like circular tectonic scars, suggesting mantle upwellings pushing and warping the crust. The absence of liquid water means that surface shapes aren't carved into river networks or coastlines, so the landscape reads as tectonic and volcanic rather than erosional. And because water is missing, one of Earth's strongest long-term carbon regulators is missing too, which loops back to why Venus stays so hot. Without water-based sinks, CO2 accumulates, and once CO2 is massive, the greenhouse effect becomes so strong the surface stays too hot for water to return, and the lock becomes permanent. You can picture that lock as a door closing slowly. Warming increases water vapor increases warming, oceans evaporate, UV breaks water molecules, hydrogen escapes, the planet dries out, CO2 remains and builds, heat trapping strengthens, the surface becomes a furnace, and at that point the system can't easily reverse because the conditions required for reversal, cool surface and liquid water, are the very things the system prevents. The cloud deck complicates the energy balance in a way that adds to Venus's dreamlike contradiction. The clouds reflect a lot of sunlight, making Venus bright and preventing even more heating at the top. But the deep atmosphere below traps heat so effectively that the surface remains extreme anyway. So Venus is a world that looks bright and cool from the outside, while being brutally hot underneath, like a gleaming lid over an oven. The radar-bright highlands add a subtle twist that keeps the story from feeling flat. Certain elevated regions appear unusually reflective in radar, which hints at chemical or mineral coatings that form under slightly different temperature-pressure conditions at high altitude, like a selective deposit line, a kind of chemical snow line without snow, reminding you that even on a globally hot planet, gradients still matter. And the crater record adds the slow time mystery. Venus has craters, but not the sheer density you'd expect if nothing ever resurfaced, suggesting the planet has been repaved on geological timescales, perhaps through episodic volcanism and tectonic deformation under a stagnant lid. Meaning Venus could have long, quiet periods punctuated by broad, resurfacing events that erase ancient scars and reset the surface age distribution. The planet's atmosphere may still be tied to that interior activity through sulfur compounds, because sulfur dioxide can be consumed by upper atmosphere chemistry, so maintaining or varying levels could imply resupply, potentially volcanic, though. Venus is hard enough to observe that certainty is rare, but the uncertainty doesn't weaken the sleep narrative, it strengthens it, because Venus is fundamentally a planet of inference, a world you know by patterns and echoes, not by clear sight. For a calm mental scene, return to the simplest loop. Venus shining as a bright point in the sky, clouds reflecting sunlight, cloud belts racing around the globe, chemistry forming acid aerosols, heat trapped below in a massive CO2 reservoir, pressure holding steady at the surface, dim diffuse light over volcanic plains, and deep below, a mantle slowly convecting, pushing up, cracking the crust into coronae and rifts, and occasionally flooding plains with lava over long ages. Nothing in that loop is quick, nothing is sharp, everything is continuous, and if you let your thoughts follow Venus's continuous motion, clouds circling, heat recycling, chemistry repeating, you end up with the only natural outcome for a mind that stops chasing novelty. It slows, softens, and drifts into sleep. Venus is the kind of planet that makes you respect how much humans can learn without ever getting a clear view, because if you judged Venus the way you judge Mars, by photos and landscapes, you'd think it's blank, but Venus is only blank in visible light, and that's the whole trick. It forces you to become patient and indirect, to accept that the planet won't reveal itself in the usual way. So you learn it by radar echoes, by chemical fingerprints, by pressure-temperature profiles, by short-lived landers that survive just long enough to send back a few minutes of truth before the environment crushes and cooks them. Venus taught us early that close doesn't mean easy, because it's right next door. Yet it's one of the hardest places to explore, not because it's far, but because it's sealed, clouds that block sight, chemistry that corrodes, pressure that destroys, heat that overwhelms electronics, and a sky that hides the surface like a permanent curtain. That curtain is why radar became the planet's language, because radio waves can pass through the cloud layer and bounce off the ground, so missions like Magellan could map Venus in a way eyes never could, turning a featureless bright disk into a textured world of plains, ridges, rifts, volcano-like constructs, and those huge circular corona that look like scars from mantle plumes pressing up from below. The calm part is realizing that radar maps are basically a kind of touch, a way of feeling the surface from orbit, and Venus becomes a planet you feel through signals instead of seeing through light, which matches the planet's whole identity. Heavy atmosphere, hidden surface, diffuse light, soft edges, blurred horizons. When landers did reach the ground, especially the old Soviet Venera landers, they proved Venus's surface isn't some abstract number on a chart. It's real rock under dim light with a low horizon and scattered stones, and those images are unsettling in a quiet way because they look ordinary at first glance. Rocks, flat ground, no dramatic canyon, no lava fountains in frame, just a silent scene. And then you remember that scene exists under crushing pressure and extreme heat, and you realize Venus doesn't need to look dramatic to be extreme. It can look calm and still be lethal, which is a perfect sleep story contradiction if you handle it right. The planet is steady, not chaotic. It's not constantly doing something loud. It's sitting in a stable equilibrium that remains hostile without ever changing its expression. This is also why Venus science is often about long-term processes rather than daily events, because Venus refuses to give you easy day-to-day variability. Its climate is locked and uniform, so the questions become big ones. How did it end up like this? How does it lose heat without plate tectonics? How often does it resurface? Is it still volcanically active? How does its super-rotating atmosphere maintain its speed? What exactly are the chemical pathways that build and recycle the sulfuric acid clouds? How does the upper atmosphere interact with the solar wind without a strong intrinsic magnetic field? And how much has the atmosphere been lost to space over billions of years? Venus turns you into someone who thinks in cycles and feedbacks, because that's what the planet is, a feedback machine. And the strongest feedback is the climate lock. CO2 traps heat, heat prevents liquid water, lack of liquid water prevents strong long-term CO2 removal, CO2 remains dominant, repeat. If early Venus had water, the runaway greenhouse pathway makes sense as a slow slide. Closer sunlight increases warmth, warmth increases evaporation, water vapor strengthens greenhouse trapping, trapping increases warmth. The system accelerates, oceans can evaporate, UV breaks water molecules high in the atmosphere, hydrogen escapes to space, the planet dries out, and once the planet is dry, the carbon cycle loses its biggest sink, allowing CO2 outgassed from the interior to accumulate until the atmosphere becomes massive and the surface becomes permanently hot. And what makes that story so sticky is that it's self-maintaining. Once the surface is hot enough, water can't condense, so the sink can't restart, and without the sink, CO2 stays. And with CO2 staying, the heat stays, so Venus becomes a stable end state. That stability shows up in the way Venus's surface temperature doesn't swing wildly from day to night, even though the planet rotates slowly, because the thick atmosphere stores heat and transports it efficiently, turning Venus into a near-uniform thermal bath. If you picture an Earth desert, the night cools fast because the air is thin and radiative loss is strong. Venus refuses to cool because the atmosphere is too dense and infrared opaque. So heat has to climb through layers before it can escape, meaning the heat exits from higher altitudes rather than directly from the surface, and the lower atmosphere remains a deep reservoir of trapped energy. Above that reservoir, the cloud deck does its own separate job, reflecting sunlight and maintaining a permanent visual lid. And within that lid, chemistry runs continuously. Sulfur compounds, trace water, sunlight, aerosol formation, droplet cycling, creating clouds that can persist because the system keeps feeding them. and at cloud-top altitudes, the winds superrotate, circling the planet quickly, carrying wave patterns and chemical contrasts around the globe like a moving tapestry. The contrast between the fast cloud belt and the slow planet beneath is one of Venus's most hypnotic facts because it makes the planet feel like it has two personalities. The ground is still and heavy, the sky is fast and looping. The ground is hidden and steady, the sky is visible and dynamic. The ground is a furnace under pressure, the sky is a circulating chemical factory, and the whole thing is tied together by energy flow, sunlight in, reflection out, heat trapped and reprocessed, circulation transporting momentum and chemistry, and slow geological outgassing and internal convection feeding the atmosphere's composition over deep time. The geology itself, as revealed by radar, supports the idea that Venus hasn't been inert. Broad plains look like lava flooding, volcano-like edifices suggest repeated eruptions, rift zones show extension, ridge belts show compression, fracture networks show stress, and corona point toward mantle plumes deforming the crust, implying a convecting interior interacting with a lithosphere that behaves differently from Earth's. If Venus lacks global plate tectonics, then its heat loss style might be episodic. Heat builds under a stagnant lid, then is released through widespread volcanism and tectonic disruption, resurfacing large areas and burying older craters, which aligns with the crater distribution that suggests the surface is not simply ancient and untouched. And because there is no liquid water to erase features through rivers and rainfall, the volcanic and tectonic shapes can remain legible in a way they might not on Earth, even while chemical alteration slowly coats and modifies rock under hot CO2 and sulfur-bearing air. That chemical alteration is another subtle theme that keeps Venus interesting without needing excitement. Because on Venus, weathering is not water-based, it's chemical and thermal, and under such conditions, certain minerals might form coatings that change reflectivity, which could be part of why some high elevations appear unusually radar bright, hinting at a kind of altitude-dependent surface chemistry, a selective stability zone that behaves like a chemical frost line. The way Venus interacts with space also matters for its long-term story. Without a strong intrinsic magnetic field like Earth's, the solar wind can interact more directly with the upper atmosphere, stripping particles and shaping an induced magnetosphere, and over long time that can contribute to atmospheric loss, especially of lighter elements, reinforcing the idea that once water was broken apart, hydrogen could escape more easily, accelerating drying. All of this makes Venus feel less like a single place, and more like a sealed system with layers and loops. And that's why the best mental image for sleep isn't a dramatic volcano or a burning landscape. It's the sensation of descent. You begin above the clouds where the planet is a bright curve and space is black. You sink into haze where sunlight becomes milky and scattered. You enter the cloud layers where acid droplets turn the world into luminous fog. You pass below the clouds into darker, denser air where light warms into orange tones. Pressure grows with every kilometer like a slow tightening. Heat rises steadily, not in spikes but in a continuous gradient. The horizon becomes close and muted because the atmosphere eats distance, and finally you arrive at the surface, a volcanic plain under dim, diffuse light, silent, steady and heavy, with the entire mass of the atmosphere pressing down like an invisible ocean. Far above, unseen from this perspective, the cloud tops race around the planet in superrotation, keeping the world's visible motion locked into an endless loop, while the surface remains trapped in the greenhouse equilibrium below. And from far away from Earth, the same planet is just a bright point in the evening, calm, steady, beautiful, like it's doing nothing at all. That's Venus's final hypnotic contradiction, a world that appears serene because its violence is not in motion or sound but in persistent physics, a planet that doesn't need to change quickly to be extreme, a planet that maintains its state, like a machine running quietly behind a curtain. And if you let your mind follow the easiest repeating patterns Venus offers, clouds circling, chemistry cycling, heat recycling, pressure holding, interior slowly convecting, your thoughts stop looking for a twist because Venus doesn't twist, it loops, and the loop is steady enough that your own mind can finally stop trying to control the next moment and just drift. Venus is also the planet that quietly proves that seeing is optional, because the more you learn about it, the more you realize that most of its personality is not visual at all, it's physical. Pressure, heat, density, chemistry, and slow time. On Earth, we fall in love with landscapes because we can see them, but on Venus, the dominant experience would be the weight of the air and the diffuse glow of the sky, a constant enclosed atmosphere that makes the world feel smaller, even if it's planet-sized, because the horizon fades and the ceiling never opens. The sky would not be blue, it would be a thick yellow-orange haze, and the sun would not be a crisp disk, it would be a brighter patch behind clouds, like a lamp behind frosted glass. Shadows would be soft, edges would blur, distance would compress, and that alone would make Venus feel like a dream space. Everything present but not sharp. The surface beneath would be rock, mostly volcanic, not because we want it to be dramatic, but because radar and lander data point that way. Plains that resemble lava flooding, volcanic constructs, fractured terrains, ridges and rifts, and the distinctive corona that look like circular tectonic scars made by mantle plumes lifting and cracking the crust. The absence of water means no river-carved valleys, no rain-polished surfaces, no ocean shorelines. So the surface story is dominated by volcanism and tectonic stress patterns rather than by erosion, and that makes Venus's geology feel like raw internal expression, like the planet's heat wrote directly onto the crust without water rewriting it later. And yet even that geology is something you mostly meet indirectly, because you don't see it through the clouds, you sense it through radar, through echoes, through brightness differences in radio wavelengths that tell you about roughness and slope and material properties. Venus becomes the planet of indirect contact. We touched it with signals, we felt it with radar, we visited it briefly with landers that survived for minutes to hours and then went silent, leaving behind the sense that Venus allows contact but not presence. That limitation is what makes its mysteries feel long and calm rather than urgent, because Venus isn't going anywhere and its state is stable, so the questions can be slow. How often does it resurface? Is volcanism ongoing? What is the true history of water loss? How does superrotation sustain itself? What exactly is the cloud chemistry doing on different timescales? How does the upper atmosphere interact with the solar wind, and what has been lost to space over billions of years? The steady climate lock remains. The simplest answer behind the planet's harshness: CO2 is massive, greenhouse trapping is extreme, the surface is hot, the surface being hot prevents liquid water. No liquid water means no strong long-term CO2 sink, so CO2 remains massive and the heat remains trapped. It's a loop that reinforces itself, and the most calming part is that it doesn't need drama to operate, it's just physics repeating. The cloud deck adds the planet's visible motion, and the fact that Venus is so reflective is almost ironic, because reflectivity is usually associated with cooling, yet here the lower atmosphere's greenhouse dominance makes the surface extreme anyway, so Venus is bright but hot, reflective but trapped, and that contradiction is part of why it feels unreal until you accept that different layers can have different energy behaviors. The top can reflect and radiate, while the bottom traps and stores. Inside the cloud layer, sulfuric acid aerosols exist in a cycle, forming where conditions allow droplets, falling and evaporating where it's warmer, and being rebuilt again by chemistry, so the clouds persist not as a one-time event, but as a maintained structure. And above, the atmosphere superrotates, circling the planet quickly, turning the cloud deck into a fast-moving, banded shroud that carries wave patterns and chemical contrasts around the globe in endless loops, while the surface underneath rotates slowly and retrograde, giving Venus that two-speed feeling. Fast sky, slow ground. The interior beneath all of it continues to matter, because mantle convection can produce upwellings that deform the crust and create features like corona. And if Venus's lithosphere behaves as a more continuous lid rather than Earth's plate mosaic, then heat loss can be episodic, with long periods of build-up and broad resurfacing events, which would explain why the crater count suggests a relatively young surface in a global sense. Those resurfacing ideas aren't about making Venus sound explosive, they're about explaining a calm puzzle, why the surface doesn't look ancient, and the answer seems to be that Venus has erased and renewed its face, not through water and wind, but through heat and lava and tectonic stress over long time. Even the possibility of altitude-dependent surface chemistry, radar-bright highlands potentially coated with minerals stable only in cooler, high-elevation conditions, adds a gentle texture to the mental image, because it means Venus still has gradients and zones even inside its uniform heat state, like subtle chemical differences that paint the terrain in invisible ways. In sleep terms, Venus works best when you keep returning to the same repeating motions: cloud top superrotation circling, aerosol chemistry building and rebuilding the cloud layers, greenhouse trapping recycling heat, dense atmosphere distributing temperature, surface sitting in steady diffuse light, interior slowly convecting and occasionally rewriting the crust, and over everything, the planet shining as a calm, bright point in our sky, as if none of its extreme physics exists. If you let your thoughts match that repetition, you can stop forcing the story forward. Because Venus isn't a story with a twist, it's a story with a steady loop. Bright clouds, hidden ground, trapped heat, fast sky, slow planet, endless cycles, and the quiet acceptance that some worlds don't change quickly. They simply persist, and persistence is the easiest rhythm to fall asleep to.